So I want to just take a moment here and talk about the plan for the end of the semester here. Okay. All right. So you guys know for this Sunday, the problem set that's due, that's up on the board, 156 to 184 in the Chapter 5 review. That's the second to last problem set. On the board. Yep. And then the final problem set is going to be from the Supplement B problems. Notice that I didn't pick all of the Supplement B problems. I just kind of went through and picked some ones that looked like good ones that were representative, because we're going to kind of go through this in not as much. I'm going to skip some parts that I find less important kind of as we go forward. So we're just going to get a little splattering of Supplement B, basically, because I have 3 class days to do it in. So we're not going to do everything, but that's the last of the problems there that are listed. That'll be the last problem set that's due. The 3-day week, we're going to start our exam review. I think juniors have retreat all 3 of those days. So like you're going to be, different people will be gone each day. But we're just going to use those as review days to work on your review packet. The maximum or the last day for the review packet turn-in is going to be at the Tuesday of exam week, and then the exams start, so we don't have a ton of time left here. But that's the rundown. Now, what could there still be that's not listed anywhere here?
Homework quiz.
There could be still one more homework quiz. We'll see whether we end up doing that or not. Everybody cool with the plan? Just like last exam, the exam review, if you turn that in beforehand, can count as some extra credit onto the exam, and you can use on the exam. Yes, sir.
So when do I gotta turn that in?
The last day is this Tuesday, the week of exam week, is like the very last day you could turn that in. Any point before that is okay, though, also. Cool? So this, I went and did like everything, like all the days we have left are on here, because it feels like that's probably helpful for you to see kind of where everything is going. Everything except for the possibility of homework quiz is up in the grade book. So there's assignments for everything that's left. At this point, we've done enough or we've done all the tests we're going to do. We're not going to do a chapter or test for B. That'll be exam only stuff, as there's just not enough days, particularly with that weird junior retreat day kind of messing everything up there. So no possibility of a chapter or test for section B. So we need to, you need to start thinking about whether you want to do a retake or take a double, because that's still an option. When you know which one you want to do, send me an email. We'll figure out a day to do the retakes if we want to do that. But usually has traditionally been a pretty small number of peoples, but we'll figure that out when it comes. Does that feel okay to you guys? That might be something we just schedule individually. Like, okay, on this day in class you'll do the review, or you'll do your retake. If you're somebody that wants to do a retake, we'll just figure that out individually, because usually it's just like 1 or 2 people. If that's not the case, we'll figure that out, but we'll just wait till that's a problem. So this next week, start thinking about which one you want to do. As soon as you know, just send me an email, tell me what you want to do, whether double or I want to retake chapter 6 or whatever chapter you want to do.
So I can send an email right now?
If you want, yeah. Leo.
So what did you say we must turn into before the final days to use on our exam?
The exam review, which I haven't given you access to yet.
Not yet. Okay.
Yeah.
Okay.
I'll probably get that up there sometime during this week. But we have, those basically 4 class days to to work on the packet. Well, it'll be 2 class periods because we meet every other day, but I blocked off all of that time specifically just to give you some chance to work on it. We can talk about a format and stuff a little bit later also, but as you guys probably saw from last semester, it was tremendously helpful having the review for the exam, so we'll do that again.
Yeah.
Cool?
Cool.
Everybody happy? Got a good idea of what's going on, what you need to do? Again, I'll keep reminding you, but as soon as you know whether you want to do a double or retake, shoot me an email and I can start entering those things in to give you a good idea of what you have going into the final. Okay. But my hope would be that, this week of, this 3-day week, I'd have all the grades basically finalized, short of maybe a retake or 2 if you elected to do a retake. But everything else I'd want to have in, and so you can see exactly where you're at. Cool? Cool. All right. So today we've got some chapter B in to do, right? We're almost there, guys. Right? Can you smell the finish? All right. So this supplement B is all about matrices. So we'll start by just defining what a matrix is. I'm going to skip kind of writing the words for some of these things because it's usually not that important, but just kind of do it by example. So typically, what we define as a matrix is like a rectangular array. So usually we use like the hard brackets to represent those. And then there's going to be like a bunch of entries in that array. So those entries typically in this class will be numbers. You might have a variable or something stuck in there at one point also, but that's typically what these entries are going to be. We like to name a matrix with a capital letter. So like I might name this matrix A. So if I want to talk about the number that would be in this spot in this particular matrix, we need a way to kind of communicate that. So the way we would name the value in this spot is we'd use the letter little a, since the matrix is named big A. And because this spot is in the first row and in the first column, we would call it A11, where we'd have a subscript of 11 there. Not 11, right? But that's like a number for the row and a number for a column. We won't do anything where you have a double-digit number of rows or columns, so it'll always look like that. Everybody's cool? So this next entry would be A12, because it's still in the first row, but now it's in the second column. What about this one down here? What would that be? Yeah, A34, because it's in the third row and the fourth column. Everybody's cool with that kind of naming convention? Okay. For a matrix, there's the first basic thing that we're going to care about is the dimension of the matrix, or sometimes we'll call it the order of the matrix. And that is always going to be written as rows by columns. So in this particular piece, how many rows do we have? 3. And how many columns do I have? 5. So this would be a 3 by 5 matrix. Rows are always written first. Columns are always written second. Everybody okay with that idea? If I said, if we wanted to talk about a square matrix, what would the dimension be for a square matrix? What do we know about the shape of a square?
It's the same on its side.
The length and width are the same, right? So if I have a square matrix, the number of rows and the number of columns would be the same. Everybody's okay with that? So example, like a 2 by 2 or a 3 by 3 or a 4 by 4 are all square matrices. Everybody feel good about this? Okay. Let's say we have 2 matrices that are equal. What does that mean for 2 matrices to be equal? Well, the dimensions have to be equal, right? If one is a 3 by 2, the other has to be a 3 by 2 also. And the corresponding entries have to be equal. So for example, Aij would have to equal Bij. Everybody's okay with that idea? So if you take the thing from A and the thing in the exact same position in B, those two things have to be equal, and it has to be that way for every entry in A and B. So for example, let's say we have these two matrices that are equal, and we want to solve for the variables here. Well, since we know the 2 matrices are equal, there's an equal sign written between them, I know that those 2 entries have to be equal. And I would know that those 2 entries have to be equal. Is everybody okay with that? So I can use that to write an equation for each of them, and then just solve. Cool so far? Okay, so that's what it means when 2 matrices are equal. The next thing we want to do is talk about how do we add 2 matrices. So if I want to add a matrix A with a matrix B, well, first thing we have to have is that the dimensions of those matrices have to be equal. And then if let's say that the sum of these 2 matrices is C, then that means that all the entries in matrix C are just going to be the sum of the corresponding entries from A and B. Now that looks kind of complicated, but it's really pretty straightforward. Basically, matrix addition works exactly the way that you would hope it would. So I'm just would add -5 and 2. And I would add 1 and -4. I'd add 0 and 2. I'd add 4 and 9. I'd add 2 and -4. And I'd add 5 and 1. So I get -3, 2, -2, -3, 13, and 6. Any questions about matrix addition? Like super straightforward, right? Works exactly the way you would hope it would work. Okay. There's actually two types of multiplication when we talk about matrices. The first is scalar multiplication. So a scalar is just a real number. So like 5 or 8 or the square root of 2 or 1/2. So if I want to multiply a number to a matrix, the dimension of the matrix doesn't matter. Let's say that this product is, we'll call that product matrix B. To get the entries in B, I'm going to just take K and multiply to the entries in A. So let's look at an example. So my resulting matrix, the first entry is just going to be 3 times -3, and 3 times 3, and 3 times 2, and 3 times 1, 3 times 6, 3 times 5, 3 times 0, 3 times 1, and 3 times -7. Or when I simplify this down, I get that. Again, super straightforward, right? The scalar multiplication is working exactly the way we'd hope. It's basically just a giant distributive thing, right? Everybody feel any questions here? Notice that the dimension of A doesn't matter. You can always do scalar multiplication. The next type of multiplication we have is matrix multiplication. Now, matrix multiplication is not always possible. The dimensions of the matrices have to be very specific. And in fact, they don't need to be equal. But what needs to happen is the columns of the matrix on the left needs to be equal to the rows of the matrix on the right. And when we do that matrix multiplication, the resultant matrix is going to have the rows from the matrix on the left, or the same number of rows, and the same number of rows as the matrix on the right. So the analogy I like to use on this is that it's, matrix multiplication is kind of like falling in love. So two people meet, and they're different on the outside, but if they're the same on the inside, they can fall in love. And when they have a baby, that baby looks a little like one parent and a little bit like the other parent. Aww. Okay, that's silly, but you won't forget. All right, so the next question becomes, okay, so I understand when I can multiply two matrices together, and we'll do some examples to kind of reinforce that. But how do I actually get the entries in this this resultant matrix C? So, oh, bleezy. Okay. So this is going to be A1R, nope, I'm sorry, R1 times B1C plus AR2 that times B2C all the way out till we have ARC times BCS. Oh, shoot. That's not right. That's not how I want to write that. My indices are all jacked up. Okay. AI1 times B1J plus AI2 times B2J plus AIS. Nope. Following along that row. So C of those times B, and following along that would be C and then J. There we go. Anyways, that's not super helpful to us, and I'll show you why with an example. Okay, so let's do an actual numeric example here. Here's my matrix A and B. What's the dimension of matrix A? Let's first make sure we can actually do this multiplication problem. What's the dimension of matrix A? 2 by 2. And what's the dimension of matrix B? 2 by 3, 2 rows and 3 columns. So I notice that the columns on matrix A are the same as the rows on matrix B, or I should say the number of columns on matrix A is the same as the number of rows in matrix B. So we can do this multiplication. Everybody's cool with that? And my resultant matrix will have what dimension? It'll also be 2 by 3. Okay, so I'm going to go ahead and write a spot for my each entry. Make that a little bit, these be a little bit longer. So not squishing everything in here too bad. Okay, so I need to fill in an entry in each one of those 6 spots, right? So this spot here would be like C11. Everybody agree with that? So C11 is going to be using row 1 from matrix A with column 1 from matrix B. So I have the first elements multiplied together plus the second elements multiplied together. Is that okay? So my next spot is C12. That's going to be using row 1 from A, and now column 2 from B. Notice that the name of the entry is telling us which row and column we need to be multiplying together. So that's really helpful to us. So we'd have 1 times 1, the first entries, plus 3 times -6, the second entries. Then we have C13, so that's going to be using row 1 from A and column 3 from B. Everybody so far so good with what we're doing? And I'm going to just keep going. Okay. Ugh, come on. All right. So now we're going to do 2, 1. So that's row 2 and column 1. And then we're going to have row 2 and column 2. And then we're going to have row 2 and column 3. Does everybody feel okay doing this? Now this is time consuming and a little tedious, but not really that hard. So what do we have here? We have -3 plus 6. So that's 3. We have 1 plus -18. So that's -17. 3 plus 15. So that's 18. -6 plus 8. That's 2. 2 plus -24, that's -22. And then 6 plus 20, that's 26. So that's our answer. Everybody feel good here? Again, my recommended way of doing this is you want to start by drawing the resultant matrix with a spot for each entry. I'd write the name for each entry below the spot so you know which row and column you're multiplying together. It makes things much, much easier. Now, I'm not always going to write it this way for you guys as we continue to go through because it's a little bit time consuming, but the first time you're learning how to do this, I think it really makes things considerably easier if you're looking at it that way. Okay. Let's do one more of these that's maybe a little bit quicker, and then we'll move on to the next set of ideas. All right. So this is my matrix A and my matrix B. What's the dimension for A going to be? 2 by 1. And the matrix, or the dimension for matrix B is 1 by 2. Can I multiply these together? Yes. Since the inner dimensions are the same. And what will the size of the resultant matrix be? 2 by 2. Okay. So C11, I'm going to take row 1 times column 1. Well, that's just two numbers multiplied together, right? And I have row 1 times column 2. Jeepers creepers here. Ah, got it. And then we have row 2 times column 1. And row 1 times column 2. So when I simplify things down, I get negative 15, 35, 12, and then negative 28. So far, so good. Into B2 we go. Hi, Grace. The next thing we want to talk about is a determinant. And the symbol we use for the determinant is typically we use the vertical bars around a matrix. This is not absolute value. I want to make that super clear. The vertical bars around a matrix does not mean absolute value. It means the determinant. If you put the vertical bars around a number, that means absolute value. If the vertical bars around a matrix, that means the determinant. We can only do the determinant on square matrices. So like a 2x2 or a 3x3 or a 4x4. We couldn't do it on a 2x3 though. Everybody's clear on that? And there's two types of determinants that we're going to ask you to be able to do, by hand anyways. That's going to be for a 2x2 and for a 3x3. Let's maybe... So let's say this is our matrix A. Then the determinant of A is going to be A times D minus B times C. So you just multiply the diagonals and subtract them. Note the order of the subtraction matters. So when you're doing your diagonals, the left to right diagonal is the one that's gets subtracted from the other one. I don't even know if that's good grammar or not. That didn't sound like it. Let's do a quick example. Okay, so if my matrix A is the matrix 4, negative 3, 2, 5, what's the determinant of A going to be? It's going to be 4 times 5 minus 2 times negative 3, or 20 minus negative 6, which is just 26. Pretty easy, right? For the 3x3 matrix, it's a little bit more complicated. So what we do is we're going to recopy the first 2 columns on the right side of my matrix. And then I'm going to multiply along the first 3 down diagonals. And we're going to add those products together. Are you cool with that? Then we're going to multiply the 3 up diagonals and subtract those products. Oops. Black. So what would you rather try to memorize? The formula that I've written below or the process that I've just described? Dude, the process is way easier to me than like that alphabet soup of confusion there. Look at all those letters. Pass on that if you ask me. You can do whatever you like. either is fine. For me, it's like I'm just going to remember how to do the diagonals and which one I'm adding and subtracting, and like that to me seems way easier to memorize than all them letters. So let's do a numeric example here. So another way we can write the determinant for a numeric example is if I put the vertical bars instead of the squared off brackets. That means that to take the determinant of this matrix, so notice that I use the straight vertical bars around my array rather than the squared off bracket. So that allows me to just simplify the notation a little bit. But I should probably, I just definitely want to point that out. Because it's easy to miss that, right? On a sheet of paper, the squared off bracket versus vertical. It's subtle, so you have to make sure that you're looking for it, but they do mean two different things. So I'll start by recopying my first two columns. When you do that, you have to recopy them on the right-hand side. And then I'm going to do the 3 down diagonals. So I'm going to have 3 times 1 times 2 plus -1 times 7 times -4, and then plus 5 times 2 times 7. Everybody's cool with that? Then I'm going to work along the bottom row and do 3 up diagonals. Okay, so what do I have here? 3 times 1 times 2 is 6, plus 1 times, or -1 times 7 times -4 is positive 28. And then 5 times 2 times 7 is 70. We have minus. -4 times 1 times 5 is -20. Then 7 times 7 is times 3 is 147, and then minus 2 times 2 times 1 is -4. So I have, well, I just do the calculator time at this point, right? Why mess around with your mental math, Mr. Kulik? It's 8:30 in the morning. The odds of you holding all those decimals or all those numbers in the proper places is, that's maybe a 50-50 proposition. It's not like you can't do it, Mr. Kulik, but it's kind of a pain in the tuchus. Everybody's okay with that? Okay, so that's how we do a determinant. The next thing I want to talk is about the multiplicative identity. So when we talk about real numbers, the multiplicative identity is 1. Because anything times 1 is itself. Everybody's cool with that? What we're interested in is what's the multiplicative identity for matrix multiplication? So what matrix can I multiply to A that I still get A back? Now the special name we're going to give that matrix is I. But we want to know, well, what is this matrix I? Well, we know that matrix I has to be a square matrix.
Has to have the same thing on the inside as A.
Right. So specifically the number of columns on A would dictate the number of rows that I would have to be, but it's going to have to be a square matrix. So that's okay. So what can we say about the entries for I? So let's just say, talking about I, that's a 2 by 2. That's what the identity matrix is for a 2 by 2. For a 3 by 3, looks like that. For a 4 by 4, it would look like that. You guys see the pattern so far? You have a ones down the main diagonal, and then zeros everywhere else. Grace? Sure. So after that observation, really you could write down any size identity matrix, right? Everybody's cool? Now what we want to talk about are multiplicative inverses. And again, this is talking about for matrix multiplication. So when we talk about real number multiplication, we say that 2 and 1/2 are multiplicative inverses, because when you multiply them together, you get the identity back, right? So what we want is, for a given matrix A, we want to know what does the matrix B have to be, that when we multiply it, we get the identity. Everybody okay with that? So the way you find this depends on the size of your matrix. The first thing, though, is that they must be square matrices. So the only one you guys are going to be responsible for doing by hand would be for a 2 by 2. And the name we give, or the symbol we're going to use for the multiplicative inverse of A is going to be A with a -1 in the corner, because we're just going to steal the same notation we would have used for real numbers, right? Like 2 and 1/2 are multiplicative inverses, and 1/2 is the same thing as 2 to the -1. So we're just kind of stealing that same notation. So we have 1 over the determinant of A times the matrix DA, or I'm sorry, D negative B negative CA. Notice that that new matrix is just kind of like a different version of A, right? We swapped the entries along that main diagonal, and then we negated the other two entries. So let's do an example. So let's say our matrix A is 4, -3, 2, 5. The first thing we have to do is we have to do the 1 over the determinant of A. Okay. So how do I find the determinant of a 2 by 2 matrix? I multiply that diagonal and then subtract that diagonal. Everybody's okay with that? And now I have to construct this new matrix here. So what is that new matrix going to be? Very good. Very good. Very good. 4. Great. Everybody feel okay? Now, 20 minus a -6 is really just 26. So now I have to do my scalar multiplication. So 5 times 1 over 26 is 5 over 26. 1 over 26 times 3 is just going to be 3 over 26. 1 over 26 times -2 is going to be -2 over 26, but that reduces to 1 over 13. And then 2 over 26 times 4 is going to be 4 over 26, but that reduces down to be 2 over 13. And so that's my final answer. All right, here's my question. Actually, let's be a little bit more general even than that. For any square matrix, does it always have an inverse? What do you guys think? Aaron's gone from yes to no.
I'm going to go back to yes.
You're going to go back to yes. Anybody else with any instinct here? The answer is no. Let's go back to the 2 by 2 formula. Actually, let's just do a specific example. Say that. Okay, so there's my matrix A. So A inverse is going to be 1 over the determinant. So how do I find the determinant here? Two times 2 minus 1 times 4. Uh-oh. What do we get here?
Well, that's a 0.
Yeah, I get 1 over 0, and then it's like... So what is the catch? It's if the determinant is 0, then A inverse does not exist. Everybody's cool with that? So that's an important piece to remember. That closes actually section 2 even. So I'm going to pause here and talk about some calculator things. So if you have your calculator with you, I invite you to take that out and follow along if you'd like. If you're a sit and watcher, you can always just sit and watch. We're recording this, so you could always come back and look at it later. So all of these matrix operations that we've done in class by hand, we can also do on our calculator. Well, that's really nice, Mr. Kulik. I know. So to do that, what we're going to do is we're going to be using the matrix menu. So to access the matrix menu, we're going to press the second button. That's the blue one. And then the X to the -1 button, because you'll see in blue above that button is the word matrix. Now, I've used my matrix menu recently so that I have stuff in here already. Probably most of yours just has A, B, C, and then blank here. Okay. So to enter a matrix into our calculator, we're going to move over to the Edit tab and select one of these. Let's just select matrix A. So I'll make matrix A, for this example, I'm just going to make it a 2 by 2 with entries 2, -5, 6, -4. So 2, -5, 6, and -4 were the entries I chose there for A. So you went to the matrix menu, you tabbed over to the Edit tab, we selected matrix A, you changed the dimension to 2 by 2, and you entered those values into by pressing the number and then enter. All right, we're going to go back to the matrix menu this time. We're going to go to the Edit tab, and we're going to change matrix B also to a 2 by 2. That's going to be the matrix 1, -3, 3, 5, or 3, -5, excuse me. Everybody's cool so far? I just press second
Okay.
and then the matrix button again. So it just takes me back to the main menu. There's not a way to like tab back out one menu.
Oh, thank
So I
you.
just had to go back and do it again. Okay. So let's say I want to do matrix A plus B. So I would just go to the matrix menu. From the names tab, I'm going to select matrix A, type in the plus button, go back to the matrix menu. From the names tab, I'll then select matrix B, press enter. And there's the calculator added A and B. I just retrieved matrix A. I pressed the matrix button. From the names tab, I just selected matrix A by pressing enter. Then typed the plus sign and went back and did the same thing to get the B. So it just looks like A plus B on my calculator. Cool. All right. What if I wanted to do like -5 times matrix A? Well, I can do the -5 times and then go back to the matrix menu. From the names tab, pick matrix A, press enter. That's scalar multiplication. Super easy. Everybody's cool? I can do A times B. So go back to the matrix menu, pick matrix A, times sign, pick matrix B, press enter. There's A times B. Everybody's cool with that? I want to point something out to you here that's quite important. If I go back to the matrix menu and pick B, and then do B times A, what do you think is going to happen? Whoa, look at that. What do you notice? Different. This is a normal part of matrix multiplication. Matrix multiplication is not commutative. A times B is not necessarily going to equal B times A. Super important you take that into account when you're typing stuff into the calculator, writing your work on your paper, that you cannot just change the order of your matrices all willy-nilly like we've been able to do with real numbers. You have to be very careful in the order in which you're doing your multiplications. Everybody's cool with that? Okay. What if I wanted to do a determinant? To get a determinant, I'm going to press second and the matrix button. This time I'm going to go over to the math tab and I'm going to choose that first option, DET. That means it's a determinant. And if I wanted to do the determinant of matrix A, I would then go back to the matrix menu, choose matrix A, close my parenthesis and press enter. There's my determinant for A. Everybody's okay with that? What if I wanted to find the inverse for matrix A? That's the last kind of operation that we've talked about doing today, right? So I can go to the matrix menu, pick matrix A, and then use the to the -1 button and press enter. There's my A inverse. I'm pretty disgusted by this big crazy decimals I'm getting. So what I can do is if I press the math button and choose the fraction command, the calculator will rewrite my matrix with fractions in it, which is like super nice. Like, oh, that's very lovely to not have to muck around with all those decimals. I think that's all the operations we've talked about so far. Can all be done on the calculator. And in fact, we didn't talk about finding like the determinant for like a 5 by 5. The expectation is you would just use your calculator to do something like that. Or to find the inverse for like a 3 by 3 or a 4 by 4. Again, the expectation is we would just use our calculator to do that.
But if it was a 2 by 2, let's find that.
Yes. So my expectation come like exam time is that you're able to do these basic matrix operations by hand as long as the instances are relatively reasonable, like a 2x2 or, or a 3x3 for a determinant, for an inverse 2x2 only. But certainly, if you're doing it by hand, why would I not start by typing it into my calculator to see what the answer is so I can kind of check my stuff along the way? For sure I am doing that. There's no reason to really get anything wrong because you'll have the formulas and you'll have a calculator. Should be really doable, right? Okay. We're going to stop here. So I think at this point you guys have seen on My Notre Dame the list of for the last problem set. That's already up there, so you could start on some of those. Anything up through what we've done today, you can do. What would that be? Let me look at my problem set here. So probably anything through 36 is doable. So obviously I didn't ask you to do all of those, but any of the problems 36 or less would be doable after today's lecture. I'm not going to go through and look at the list again and be like, okay, so that is blah, blah, numbers, blah, blah, like you guys get it. You guys know what less than 36 means. Any questions about today or what's going on? Eric? Let's say that the last day for that would be that Thursday or Friday on the Wednesday or Thursday on that 3-day week. So give me a day or two to get the stuff in before exams start. But let's say that. And I'll collect all these points together and get them into one note in a, like I made that tab for the juniors, or for the seniors, I'll make another tab for you guys and collect all these details into one place. Probably at some point next week, we'll get that all in there. Okie dokies. We feel all right with the end of the semester, what's going on, what you're expected to do. All right. Sounds good.